Designing a routing protocol deployment. This section first describes why certain protocols are suitable for specific modules in the enterprise architecture. After that, a discussion of the following advanced routing features like redistribution, filtering, and summarization will be covered. Routing protocols in the enterprise architecture. Okay, so the key point here is that EIGRP and OSPF both adapt quickly to changes and have short convergence times. Therefore, they are suitable for use in the campus core. Okay, we just have to remember that EIGRP is running only on Cisco devices. So if you are using hybrid or different vendors, okay, or different brands of routers or network devices on your network, then OSPF is a good choice. Okay, so building access within the enterprise campus, distribution core, so that is where we apply EIGRP or OSPF. Now, the decision of whether to use EIGRP or OSPF should be based on the underlying physical topology, IP addressing, equipment used, and possible issues related to routing protocol in particular situation. Okay, now this figure here just illustrates routing protocols in the enterprise architecture, including those recommended for campus core. All right, so internet connectivity, we can use static routing, okay, or BGP. Now, when to use BGP? If you are multi-homed, meaning the organization is connected to different ISPs or more than one ISP, okay, then it is recommended to use BGP. If your organization is single-homed to a single ISP, then we can deploy and use static. Okay. So within the enterprise, you can use also EIGRP or OSPF. Same thing with the site-to-site, VPN, one-end man. Okay. Enterprise branch, within the branch, okay, you can use EIGRP or OSPF there. Okay. For connectivity, well, you can use a VPN. Route redistribution. So the following are the possible reasons why you might need multiple routing protocols running at the same time within your network. So basically, the use of different routing protocols in a single autonomous or within the organization is not recommended. Now, that happens sometimes when two organizations merged and these two organizations uses different routing protocols, then that's the time we have to use route redistribution. Okay, so political issues are included. That's why there are some organizations running different routing protocols, or maybe they are using different vendors. Okay, now for communications within the Cisco devices, they are using EIGRP. For communications within non-Cisco devices, they are using OSPF. And there is a need for this group of networks to redistribute or to connect, then that is where route redistribution comes into play. Okay? So you are migrating from an older IGP, okay, to a new IGP. Multiple redistribution boundaries might exist until the new protocol has displaced the old protocol completely. That's one of the reasons. Okay? So running multiple routing protocols during the migration is effectively the same as network that has multiple routing protocols running as part of its design. So you want to use another protocol but have to keep the old routing protocols because maybe of the host system's needs. For example, host-based or Unix host-based systems or routers might run only on RIP. Then you don't have a choice but to redistribute. Okay, some departments might not want to upgrade their routers to support a new routing protocol. Okay, so if you have a mixed vendor environment, as I have mentioned earlier, you can use the Cisco proprietary EIGRP routing protocol in the Cisco portion of the network and use the common standard-based routing protocol such as OSPF to communicate with non-Cisco devices. So that is when we use or consider the utilization of route redistribution. Now let's talk about the route redistribution direction. So redistribution is often applied between the campus core and the enterprise edge protocols. Now, as shown here in the figure, redistribution is possible in two ways. Okay? So you've got a one-way route redistribution. Routing information is redistributed from one routing protocol or domain to another, but not vice versa. So static or default routes are required in the opposite direction to provide connectivity. Okay? Now, for the two-way route redistribution, routing information is distributed from one routing protocol or domain to another, and vice versa. So static or default routes are not required because all routing information is passed between two entities. How about route redistribution in the enterprise network? So redistribution is needed in the building distribution layer when different routing protocols or domains exist in the building access layer and the campus core. So redistribution might also be needed when the campus core and the enterprise edge, including to and from one module routers, from static or BGP routes in the internet connectivity module and from static routes in the remote access and VPN module. Now, this figure here shows a sample enterprise network with redistribution points throughout. Okay, so in this example, some remote sites requires connectivity to the server farm. Okay, therefore, one-way redistribution is performed to inject routes from these remote sites into the campus core. Okay, now some remote sites requires connectivity to the entire network. This is provided by a two-way redistribution. Otherwise, static routes would have to be configured on the campus core. Now, the building distribution layer propagates only on a default route down to the building access layer, whereas the building access layer advertises its own subnets to the building distribution layer. Redistribution might also be necessary in the remote access and VPN and internet connectivity modules. Okay? Now, for a remote access and VPN module with static routing, static routes are injected into the campus core. Okay? Now, in the opposite direction, default routes provide connectivity for remote users. In internet connectivity module with only one exit point, the exit point is the default route to traffic destined to the internet and is propagated through the core routing protocol. Now, if multiple exit points towards the multiple ISPs exist, BGP provides internet connectivity and redistribution can be used. Route filtering. So as mentioned, route filtering might be required when redistributing routes. Route filtering prevents the advertisement or acceptance of certain routes through the routing domain. So filtering can be configured as follows. So on a routing domain boundary where redistribution occurs, within the routing domain to isolate some parts of the network from other parts, to limit routing traffic from untrusted external domains, filtering is used with route redistribution, primarily to prevent suboptimal routing and routing loops that might occur when routes are redistributed at multiple redistribution points. So route filtering is also used to prevent routes about certain networks, such as private IP address space, from being sent or to received from remote sites. Okay, so the next one would be route summarization. So route summarization, which is also called route aggregation or supernetting. So in route summarization, a single summary address in the routing table represents a set of routes. Summarization reduces the routing update traffic, the number of routes in the routing table, and the overall router overhead in the router receiving the routes. Now, what are the benefits of route summarization? So a large flat network is not scalable because routing traffic consumes considerable network resources. When a network change occurs, it is propagated throughout the network, which requires processing time for route recomputation and bandwidth to propagate routing updates. So for route summarization, so for example, from our given topology here, okay, so you've got the San Francisco campus, the Denver region, and the Houston region. So route summarization should be on a router or the edge router connected to other network. In this case, this router here connects the Denver region to the San Francisco campus. So therefore, this is where we perform route summarization. So instead of propagating all the networks within the Denver region, we just have to summarize these IP addresses here and come up with a single 172.16.8.0/22 to represent the entire network on the Denver region. So you could do the same for Houston going to San Francisco. So recommended practice, summarize at the distribution layer. So it is recommended practice to configure summarization in a large network from the distribution layer towards the core as illustrated on this figure. Okay. Now, the distribution layer should summarize all networks on all interfaces towards the campus core. WAN connectivity and remote access points should be summarized towards the core also. For example, remote subnets could be summarized into major networks, and only those major networks would be advertised to the core. Now, implementing summarization at the distribution layer optimizes the convergence process. For example, if a link to an access layer device goes down, return traffic to that device is dropped at the distribution layer until the routing protocol converges. So summarizing also limits the number of peers that an EIGRP router must query, or the number of LSAs that an OSPF router must process, which also reduces the convergence time. Recommended practice, passive interfaces for IGP at access layer. So another recommended practice is to limit unnecessary peering across the access layer. Now from the figure, the distribution multi-layer switches are directly connected to each other, okay, and are also interconnected with 3 access layer switches, each having 4 VLANs, for instance. Now by default, the distribution layer devices send routing updates and attempt to peer with remote distribution layer devices across the links from the access switches on every VLAN. Now, having the distribution switches form neighbor relationship over these 12 access layer connections provides no benefit and wastes of resources, including CPU processing time and memory. So therefore, the interfaces on the distribution layer devices towards the access layer should be configured as passive interface under the routing protocol configuration. Okay, this suppresses the advertisements of routing updates for that routing protocol on those interfaces. Now, summarizing designing a routing protocol deployment. Large networks may implement multiple protocols for different modules on the Cisco Enterprise architecture. Advanced routing features such as redistribution, filtering, and summarization allows multiple routing protocols to coexist and provide greater scalability. Redistribution between different routing protocols passes routing knowledge from one protocol to another. Route filtering prevents advertisement of certain routes through the routing domain. Route summarization and an IP hierarchy reduce routing traffic and unnecessary route recomputation. So IP addressing and routing review. So that includes defining the IP addressing requirements, develop hierarchical IP addressing plan, use private addresses inside or within the organization, use public addresses facing the internet, use NAT or PAT for translation as needed, develop a plan for deploying DHCP and DNS, use EIGRP or OSPF based on organizational requirements, and implement recommended practices, including redistribution, filtering, and summarization. Now, let us summarize the module. We've talked about designing IP addressing and selecting routing protocols. IP address structure and IP address types have a large impact on the address plan for both IPv4 and IPv6. EIGRP and OSPF are the recommended IGPs for the enterprise. Advanced routing features such as redistribution, filtering, and summarization supports scalability and multiple routing protocols. That's the end of this video lecture. See you on the next video. Have a great day.